So now we're going to talk about the structure of different molecules, and we've already talked about this a little bit in the chapter 1. The structure of an alkyl halide is the same essentially as the structure of an alkane, with a halogen replacing a hydrogen atom. The halogen has the same basic geometry as the hydrogen atom, but it does have different hybridization. But because it only makes one bond, it's still the geometry of the halogen atom itself is linear. And the atoms are larger in size, and therefore the bonds are longer and weaker than a bond to hydrogen. As the atom size increases, the bonds become even longer and weaker. And so since fluorine is the smallest, it has the shortest and strongest bond. And the iodide is the largest, it has the longest and weakest bond. Alcohols are structured similar to water. If the R group, which represents the carbons bonded to the alcohol, were a hydrogen, we would be looking at a water molecule right now. And so essentially, alcohol has the structure like water. It has a bent geometry about the oxygen, which has 2 bonding domains and 2 non-bonding electron domains. The electrostatic potential map for the alcohol shows the electron distribution with negative electron density focused at the oxygen and positive electron density focused at the hydrogen off of the oxygen. So this is essentially showing us partial negative and partial positive charges of our polar bond. The structure of an ether also resembles water. In this case, instead of 2 hydrogens being bonded to oxygen, 2 carbons are being bonded to oxygen. But the geometry of the oxygen atom itself is identical to the geometry that the oxygen has in water. In this case, because the oxygen is not bonded to a hydrogen, the molecule is actually less polar because the electronegativity difference between carbon and oxygen is less than the electronegativity difference between oxygen and hydrogen. Ethers are less polar than alcohols. Than alcohols. An ether is structurally like water, and it has both hydrogens replaced by R groups. The oxygen has 4 electron domains, 2 bonding and 2 non-bonding. So 4 electron domains means that the oxygen is sp3 hybridized, and having 2 non-bonding domains and 2 bonding domains indicates that the molecular geometry is called bent, the same as the molecular geometry of water. Structures of amines. The N in an amine has the same geometry as the N in ammonia, but one of the hydrogen atoms of the NH3 ammonia is replaced by a bond to carbon. So we've replaced one of the NH3 hydrogens with a bond to carbon and generated methylamine. We can also make dimethylamine and trimethylamine. As the hydrogen atoms, as we replace the hydrogen atoms bonded to nitrogen With carbon, we are removing a position at which hydrogen bonds could be formed. Remember, a hydrogen bond is a bond between an NH group of one molecule and an NO or F of another molecule. Or it could also be an OH bond of one molecule interacting with an NO or F of another molecule. We're going to talk about hydrogen bonds in a later slide on this chapter. As the hydrogens are replaced by carbon, the electron density of the nitrogen becomes slightly smaller because the electronegativity between difference of N to H is smaller than the electronegativity difference of N to C. The molecular geometry of the nitrogen is sp3. It has 4 electron domains. Of the 4 electron domains, 1 is non-bonding and 3 are bonding, and this has a molecular geometry of trigonopyramidal. One non-bonding ed and 3 bonding ed. Boiling points. The greater the attractive forces between molecules, the higher the boiling point. So as attractive forces increase, then the boiling point of the molecules of similar structure increases. London dispersion forces are the weakest type of attractive forces we will discuss. Dipole-dipole interactions are a middle strength attractive force, and in this class, the strongest attractive force we will experience is hydrogen bonds. Note that we will not be having to deal with ion dipole interactions in this course. So these are rarely observed in organic. And your book does not discuss them. Boiling points. For alkanes, the only type of attractive force are London dispersion forces. And as the number of carbons increases, the boiling point will increase due to the increased amount of London dispersion forces. The more atoms you have, the more London dispersion force will occur. The greater the surface area of the molecule, the higher the boiling point. As the carbon number increases, the surface area increases, and so does the boiling point. Now, I've already discussed earlier in this chapter that a branched molecule of butane would have a smaller surface area than an unbranched molecule of butane. So the more molecules that have the same molecular formula can be differentiated by boiling point by differentiating straight chain from branched chain. So branching lowers the boiling point. We have comparison of pentane, 2-methyl butane, and 2,2-dimethyl propane. All of these molecules have the same molecular formula. C5H12. So the mass are identical, and that is not what is determining boiling point. In this case, what is determining boiling point is overall surface area. As a straight chain has a larger surface area than a branch chain, and therefore branch chain has lower boiling point. And you can look at the physical data. Pentane straight chain has a boiling point of 36.1. Having one methyl branch at carbon 2 decreases the boiling point to 27.9, and having two methyl branches decreases the boiling point to 9.5 degrees Celsius. For dipole-dipole interactions, what we have in this case are interactions between molecules that have polar bonds. An interaction between molecules that have polar bonds. So between two molecules, at least two, each of which has a polar bond. Or a non-zero dipole moment. So our example here are a carbon bonded to what we're calling Z, which could be nitrogen, oxygen, fluorine, chlorine, or bromine. And a number of other atoms which have an electronegativity difference from carbon that is greater than 0.5. As long as the electronegativity difference from carbon is greater than 0.5, we will have a polar bond. So we have a map here demonstrating dipole-dipole interaction. And what these little pill looks like, this is actually one molecule, and it is showing the dipole moment of the molecule, that one side is negative, more negative than the other side, which is positive. The molecules orient themselves in solution so that the positive end of the dipole of one molecule interacts with the negative end of the dipole of another molecule due to electrostatic attraction of a negative to a positive charge. Dipole-dipole interactions are stronger than London dispersion forces because the dipole moment is permanent. In London dispersion forces, there is a temporary dipole moment which changes as soon as the electrons move. For polar bonds, the dipole moment is permanent and will not change, and therefore dipole-dipole interactions are stronger than London dispersion forces. Comparing a London dispersion force molecule to a molecule with dipole moments, the boiling point of cyclopentane is 49.3. When we have a polar oxygen in the ring, the boiling point increases to 65 degrees Celsius. And tetrahydrofuran, having polar bonds, will have two types of interactions with other molecules of tetrahydrofuran: London dispersion forces and dipole-dipole interactions. The types of intermolecular forces are cumulative. If a molecule has dipole-dipole interactions, it will always also have London dispersion forces. In fact, all molecules everywhere have London dispersion force intermolecular interactions. But since not all molecules are polar, not all molecules have dipole-dipole interactions. Only polar molecules that have polar bonds, will have dipole-dipole interactions with other molecules that have polar bonds. Comparing boiling points of molecules that have so this chart is specifically comparing molecules with the same number of row 1 atoms. Either we have 3 carbons, 2 carbons and 1 oxygen, 2 carbons and 1 oxygen, or 2 carbons and 1 nitrogen. The relative mass of these molecules is similar. The relative size is similar. Um, so that is a very important distinction. They must be, to compare, we should have molecules of the relatively the same size and mass, and the number of row 1 atoms should be relatively equivalent. Any molecule that had more row 1 atoms, 4 carbons, 2 carbons and 2 oxygens, etc., would likely have a larger boiling point than molecules that have only 3 row 1 atoms. It gets more complicated to compare molecules with 3 atoms to row 1 atoms to molecules with 4 row 1 atoms, unless we're comparing something such as 4 carbons to 2 carbons and 2 oxygens. Then 2 carbons and 2 oxygens would clearly be more polar than 4 carbons. Okay, so let's look at the data given in this chart. When we have 3 carbons, the boiling point is negative 42.1. If we have 2 carbons and 1 oxygen, the boiling point increases to negative 23.7. The intermolecular force experienced by only carbons is dispersion forces. When we add an oxygen and we add polar bonds, we now have dipole-dipole interactions and dispersion forces. Alcohols, we go from having a COC to CCAO, and the type of intermolecular interactions that OH groups can have are hydrogen bonding. And hydrogen bonding is the strongest intermolecular attraction we're going to study. It's greater than dipole-dipole forces, and so the boiling point is higher, 78 degrees. Amines also have the ability to hydrogen bond, and so we expect the boiling point to be higher than the ether or the alkane. But if you notice that the boiling point of the amine is less than the boiling point of the alcohol, and that is because the dipole moment, or the dipole between carbon and nitrogen and hydrogen, is less than the dipole of carbon to oxygen or oxygen to hydrogen. So the relative polarity of an alcohol is greater than the polarity of the amine. It has a higher boiling point because it is more polar than an amine. In the second row of the table, we're comparing 4 carbon molecules, and they follow the same trend. If we compare 4 carbon hydrocarbon to an ether, the boiling point increases. When we go from dispersion to dipole-dipole, when we go from dipole-dipole to hydrogen bonding, the boiling point increases again. And for the 2 molecules that can hydrogen bond, the alcohol and the amine, the more polar of the 2 molecules has the higher boiling point, the alcohol. Comparing boiling points as number of carbons increases for having hydrogen, fluorine, chlorine, bromine, or iodine at the position indicated by Y. For a 1 carbon molecule, when we go from hydrogen to fluorine, the most electronegative atom on the periodic table, the boiling point increases. When we move to chlorine, which has a longer and weaker bond, from carbon to chlorine, the boiling point increases again, even though the polarity is less. The strength of the bond is also impacting boiling point. Or in this case, we're talking about the polarizability. The larger the atom, the more polarizable the electron, which is actually an increase in dispersion forces. So it has stronger dispersion. And the difference in that dispersion force is having a very large impact on the boiling point. So for more polarizable, we have higher boiling. And this is something that increases as you go down a group. So polarizability increases down a group. Okay. So, and as carbon increases, you also see that the boiling point is increasing, but just noting that as you go down a group on the periodic table from fluorine to iodine, the boiling point increases because the size of the halogen increases and the polarizability of the halogen increases, which increases London dispersion force for that atom. Here's a brief quiz over some of the topics that we covered in this chapter. Think of this as a practice quiz. It's not graded, but you can answer these questions and then check back with me to see if you answered them correctly. I would be happy to provide feedback. Hydrogen bonds. Oh. Hydrogen bonds are bonds that are represented by a blue dash. They are not an actual physical bond, but they are a measurable intermolecular force. So a hydrogen bond is generated because of the large disparity of the dipole moment between hydrogen and oxygen. It has a very large dipole, and the oxygen will be partially negative while the hydrogen is partially positive. The partially negative oxygen of one molecule that has an OH bond, covalent bond, will be attracted to the partially positive hydrogen of another molecule that has an OH covalent bond. I like to think of this as an H sandwich. We have an oxygen of one molecule making a partial bond to a hydrogen that is covalently bonded to an oxygen in another molecule. This can also be that an NHN sandwich. So the dipole moment of N to H allows for the same interaction with amines. So for a hydrogen bond to exist, you need one of the following combinations. O dash 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 H, covalent bond O. We can put the dashes in a different color so that it's clear it's not the same thing. Dash dash dash. We could have O dash 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 H, covalent bond N, which has one lone pair. We could have O dash 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 H, covalent bond F. And then for this, we have several other possibilities. So repeat the same table, but instead of oxygen on the left hand of the hydrogen bond, do the same thing with nitrogen. So N dash dash dash. And then fill in the same things in the right-hand side. And then the third type would be to have fluorine instead of nitrogen as the atom on one side of the hydrogen bond. Because fluorine is generally not as reactive, and we don't have fluorine reacting with molecules very often, and so we're not going to have to worry about the type of hydrogen bond formed with fluorine atoms. Hydrogen bonds are stronger than dipole-dipole interactions, and so they will have a larger effect on boiling point. So if you're comparing molecules of similar size and atom number, then the molecule that can hydrogen bond will have the highest boiling point, and the molecule that is not capable of hydrogen bonding or of polar bonds will have the lowest boiling point. If it only contains carbon and hydrogen, it's more likely to have a low boiling point. Hydrogen bonding occurs in water. You can see here that they specifically indicate that one water molecule can make 4 hydrogen bonds. And why is that? What they're not showing is that for every hydrogen covalently bonded to oxygen, we can have 1 hydrogen bond, but we can also have 1 hydrogen bond. Hey, why can't I erase? Okay, hold on a second. Keep, draw, erase. Big screen. Oh, what color do you guys want the lone pair? Let's do purple lone pair. We can also have 1 hydrogen bond for every lone pair on an oxygen. And that lone pair is providing the specific interaction to form a hydrogen bond with the hydrogen of another molecule of water. So when you count how many hydrogen bonds a molecule is capable of making, you should, well, that's annoying. That's really, really irritating. Okay. 1, counting how many hydrogen bonds can be made. H bonds possible. And the more H bonds possible, the higher the boiling point, theoretically, of molecules of comparative size. So you count how many OH, NH, or HF bonds there are. So covalent bonds from, so if you count the number of covalent bonds from O, N, or F to H, each of those bonds is going to make 1 hydrogen bond to another molecule. And count the number of lone pairs LP lone pairs on O, N, or F, because each lone pair can make a hydrogen bond to a covalent HO, HN, or HF in another molecule. So we can show here that for each covalent bond from oxygen to hydrogen, we form one hydrogen bond, and for each lone pair of the oxygen, we form one hydrogen bond.